In this section, we'll be looking at air resistance. Now, thus far we have ignored air resistance for projectile motion problems, and we've said that in many problems that is acceptable and we will still get pretty good approximations for the motion of the object, ignoring air resistance. But if we want to have a closer look at the motion of an object, or we want to find our understanding of it, then we do need to take air resistance into account, and that's what we're going to be doing in this section. Now, air resistance is a drag force, and it's caused by the object as it travels through the air colliding with the air molecules. So the first thing to know is that because it's a drag force, so the force is always opposite the motion. The size of the force, the size of air resistance, depends on two things. The first is the shape of the object. And so in this case, you could imagine that the surface area that is pointed in the direction of travel might really matter. So for instance, we know that aerodynamic shapes that are pointed tend to travel with less air resistance, and really blunt objects tend to have a lot more air resistance. The other thing that affects it is the speed of the object. And I think you know this, that if you are traveling in a car and you stick your hand out the window and the car is traveling slowly, you don't feel nearly the same force as if you were, say, driving on the highway and stick your hand out the window, and there you feel a very significant force of air resistance. And so those are the two things that air resistance depends on. And so we're going to use those two properties to kind of understand a few things about air resistance and how it might affect the motion of an object. So the first thing we want to do is look at what happens when an object falls with air resistance. So instead of falling freely, this time the object's going to fall, and we are going to take into account air resistance. So what happens with this object? Well, we're going to look at it in terms of step by step and kind of looking at how the force acts on it through free body diagrams. So the first thing that happens is the object falls because of gravity, of the force of gravity. Okay. So at the beginning, because air resistance depends on the speed of the object, if we drop the object from rest, which is to say it has no velocity to begin with, then what we know is that at the very beginning, its free body diagram is going to look like this, where the only force acting on it is gravity. Now, as the object picks up speed, air resistance increases. Okay, and so as the object falls, now all of a sudden, maybe it's partway down, and so we still have the same force of gravity, but now it's starting to pick up a little bit more air resistance. So as long as the force of the air is less than the force of gravity, the object continues to accelerate downwards. Okay, and so as it speeds up, the force of the air increases. Okay, but this won't go on forever. This happens until F of the air gets big enough that it actually equals the size of the force of gravity. Okay. And so what the free body diagram looks like at this point is at this point you have force of gravity acting downwards and the force of the air acting upwards, and they're exactly the same size. And if they're the exact same size, then we have no unbalanced force, and so there is no more acceleration. And so at this point, the object falls with a constant velocity. And this constant velocity has a name. It's called terminal velocity. Okay. And so at that point, what we see is from there on out, there will be constant velocity motion. Okay? So that is what happens as the object falls. Now, how do we understand this? So let's take a minute to understand how this might affect some of the things that we've seen before in problems, okay? So one of the things that we noticed before is that both in projectile motion and when we were looking at basic freefall problems where the ball moved straight up and straight down, that the ball spent just as much time on the way up to max height as it did on the way down. Now, how will that change if air resistance is there? Well, no longer are we going to have the same symmetries that we had before. And in fact, what you know, if you throw, say, a piece of paper up in the air, is that it's going to come very quickly to a stop, and then it's going to gradually fall down. So we know it spends less time on the way up. And so what's going on here? Well, let's go ahead and draw a free body diagram about what's happening on the way up versus on the way down. So on the way up, again, we have the force of gravity, and that same force of gravity acts on the way down. But on the way up, what happens is we have that the force of air resistance acts downwards because the object is traveling upwards, and air resistance is a drag force, so it always acts opposite the direction of motion. So in this case, the force of the air acts downwards. On the way down, the opposite happens. The force of the air acts upwards. Well, what does this mean? Well, if we have both gravity and air resistance acting on the way up, we want to understand that what that means in terms of motion. And so that means we can't talk about forces. We need to talk about kinematic variables, which is to say acceleration. And so on the way up, what we realize is that the acceleration must be bigger, at least in size, much bigger than 9.8 meters per second squared. And that's because we have both gravity and the air resistance acting downwards. So we know that it's going to act with gravity, and together they're going to be able to create an acceleration that's bigger than 9.8 meters per second squared. On the way down, the opposite happens. Because air resistance acts opposite the direction of motion, then in this case what we realize is that the force of gravity and the force of air act opposite each other, and so the object is not going to accelerate at the same rate as it would if there was no air resistance. So the acceleration is less than 9.8 meters per second squared. When we're talking about the size of the air resistance, of course it's downward, so it's going to be negative. And so what does that mean? Well, because A is bigger on the way up, it's going to come to a stop quicker than it would reach that speed or reach that position on the way down. Okay? And so what we see is that, again, by looking at this, we can see that this force, the fact that it's a drag force, really results in some of the lack of symmetries that we see when we look at air resistance. Now, the final example here is kind of the most important thing to look at when we start talking about air resistance. So we said before that all objects fall at the same rate is a statement that we make when we're talking about all objects fall at the same rate when there is no air resistance. But as we know, heavier objects do fall faster than lighter objects. you drop a book and a piece of paper at the same time, it's absolutely clear that they do not fall at the same rate, that the heavier object falls faster than the lighter object. So let's try and understand why that's the case. And so to do that, I'm going to pretend, or let's look at a, say, 1 kilogram object and a 10 kilogram object. And so what we want to do is we want to look at both as they fall. So for the 1 kilogram object, I'm going to again draw a free body diagram, and I'm also going to draw a free body diagram for the 10 kilogram object. Now, because the 1 kilogram object has 1 kilogram, the force of gravity is the mass times 9.8, which is 9.8 newtons. Now for the 10 kilogram object, the force of gravity is much bigger. It's 10 times 9.8, which is 98 newtons. Now at this point, do not make the mistake of thinking, oh, look how big the force is on the 10 kilogram object, that's why it falls faster. Because we know the difference is not due to gravity, and the reason we know that is that it is not forces that determine how fast something falls, it's their acceleration. And if we look at the acceleration in both cases, 9.8 over 1, its mass, or 98 over 10, we're going to see that the acceleration in both cases is our familiar 9.8 meters per second squared. So what we do need to do is look at the difference that the air resistance acts on each object. And to do that, let's assume that they're the same shape, okay, as it said, but they have different masses. And let's assume that at some moment they're traveling the same speed. But if they're the same shape and the same speed, we know that the force of the air on them is equal. Let's just say it's 1 Newton. And the reason it's equal is that, as we said, that the force depends on the shape and the speed. It does not depend on the mass. And that's what's significant here. Because the force depends on the shape and the speed, if they're the same shape and the same speed, then they'll have the same drag force. But what does that mean about the accelerations of these objects? Well, I think you can see that if we look in this y direction and apply Newton's second law, what you get is that you have the force of the air acting upwards minus the force of gravity acting downwards. And for this first object, that's 1 times a. So you get 1 minus 9.8 equals a. And so this is negative 8.8 meters per second squared equals a. That's the acceleration for the 1 kilogram object. But for the 10 kilogram object, if we do the same thing, what we realize is that 1 minus 98 equals 10a, and this says that negative 97 equals 10a, which is to say negative 9.7 meters per second squared is equal to the acceleration. And this calculation is really representative of what's going on. As you can see, the 10 kilogram object has an acceleration downwards of 9.7 meters per second squared. The 1 kilogram object has an acceleration downwards of 8.8 meters per second squared. And I think you can clearly conclude here that because the acceleration is greater downwards for the 10 kilogram object, that it's going to fall faster. And conceptually, this calculation helps us understand what's going on. Gravity on both of these objects is going to have the same effect, which is to say the acceleration for both of them will be 9.8 meters per second squared. But the difference here is that we realize that if the same drag force, in this case 1 Newton, acts on a 1 kilogram object and a 10 kilogram object, because of Newton's second law, what we know is that that drag force will have more of an effect on an object with a smaller mass, which is to say that we have to switch our perspective. The reason the heavier object falls faster is because air resistance is more effective. That 1 Newton force has much more of an effect at holding up the 1 kilogram object than it does the 10 kilogram object. And this is really the difference. Air resistance, because it acts on an object and depends only on the size and the shape, will not depend on the mass of the object. And so if the same amount of air resistance acts on a heavy object and a light object, air resistance will be much more effective at holding up a light object than it will a heavy object, and that will keep the light object in the air longer than the heavier object, which is to say, the heavier object will fall faster than the lighter object.